So we continue to close the veil and wait for the final bit of ash to fall, allowing us more time to reflect. And we find that reactions barely begin with all of their components in their standard states. So we need to find a relationship from our previous expression for when delta G is not in its standard state, or when delta G is in non-standard conditions. So when you have a delta G that's not in its standard state, you will not see the degree symbol. Essentially, we're going from delta G naught to delta G, and we need to be able to figure out an expression that's going to help us with that. How do we find that expression? Well, the derivation process is very long. I'm not going to put you through it. Essentially, you're deriving the change in free energy expression with our delta G naught expression that we got before in relationship to equilibrium. When you put these two expressions together, we can finally get delta G under non-standard conditions, which is going to equal to delta G naught plus RT natural log of Q. Again, we're not at standard conditions, so we can't just say, oh, we're at equilibrium anymore. We're using a Q value here. So now we can figure out our delta G under any condition that is given. Now, of course, if we focus on standard states again, then the delta G value is going to equal to delta G naught plus RT natural log of 1, because our Q value is equal to 1. And we know if our Q value is equal to 1, this entire portion here is equal to 0. So we essentially have delta G naught plus 0. That means at standard states, the reason why we're able to interchangeably use delta G without a degree symbol and delta G with the degree symbol is because at standard states, delta G under non-standard conditions is going to still equal delta G naught. So let's get back to Dad's card from some examples, folks, using our new non-standard state expression. All right, we're back at Dad's car, and this overall question is saying that we're going to be using molecular scenes to find delta G under non-standard conditions for a reaction at non-standard conditions, okay? So this says these molecular scenes represent 3 mixtures in which A2, which are black, like we see here, and B2, which are green, like we see here, are forming AB, which are going to be the black and green ones here. Each molecule represents 0.10 atmospheres. The equation is A2 gas plus B2 gas is in equilibrium to form 2AB. And they give us a delta G naught value of negative 3.4 kilojoules per mole. For letter A, they said mixture 1 is at equilibrium, calculate K. So we're only going to focus on the molecular scene here. And then for letter B, it said which mixture has the most negative delta G value and which has the most positive. So that's going to mean that we're going to be focused on 2 and 3 because we already would have our value for number 1. Let's go ahead and start with letter A. But first, I'm going to assess my molecular scene. So they tell me that A2 is black, B2 is green, and AB is going to be green and black. So for this first scene here, mixture number 1, I have 2 A2 molecules and 2 B2 molecules. Now, because each molecule is 0.10 atmospheres, I'm going to take 2 and multiply by 0.10 and 2 and multiply by 0.10 for B2. For AB, I have 4 molecules here. So I'm going to take 4 and multiply by 0.10 atmospheres for AB. I'll do the same thing for mixtures 2 and 3. For mixture 2, I have 2 AB molecules, 3 A2 and B2 molecules. And for mixture 3, I have 6 AB molecules and 1 A2 and 1 B2 molecule. So for letter A, if I'm only focused on mixture number 1, I can use these numbers and, of course, my value that's given to solve for K. Now, what is K? K is the equilibrium mass action expression, right? So that means I'm going to take my product concentration, or here we're talking about our product partial pressures, and divide it by my reactant's partial pressure. And I get K is equal to the partial pressure of AB squared divided by the partial pressure of A2 multiplied by the partial pressure of B2. And of course, K is going to equal to Q because we are at equilibrium. I'm going to go ahead and make sure I plug in all my values. Now to get the partial pressure of AB, remember we had to take 4 and multiply it by 0.10 atmosphere. Same thing for all of our expressions here, all of our different molecules. We have to multiply the number that we have by 0.10 atmospheres. So that means our K expression is going to be 0.40 atmospheres squared divided by 0.20 atmospheres multiplied by 0.20 atmospheres. So overall, our K value is going to equal to 0.16 divided by 0.04. And now I get a value of 4.0. Now, for letter B, they're going to say which mixture has the most negative delta G and which has the most positive. So if we're going to use mixture 1, we already know our K value, which is awesome. So we have to basically figure out what expression we're going to use. There's only one expression that's going to help us understand delta G, and that is our non-standard conditions expression. So let's get to it. So we can remember our delta G expression for non-standard conditions is equal to delta G naught plus RT natural log of K. We just figured out our K value, which is 4.0. We know our R value is 8.314 joules per mole Kelvin. The delta G naught value is given at negative 3.4 kilojoules per mole. And so we have to be able to solve for our non-standard delta G. In order to do that, we need to figure out what our temperature is going to be. And so to solve for temperature, we must use the variables or the numbers we actually have. So we have delta G naught, we know our R value is 8.314, and we have our K value. Therefore, we can use our delta G naught expression to solve for T. So if I'm going to isolate T by itself, then I'm going to take and divide by negative R natural log of K. So I'm going to do that to both sides. Therefore, my temperature is equal to delta G naught divided by negative R natural log of K. And all I would do now is plug in my values to solve for temperature. Once I have my temperature, I can use that temperature for all my calculations to solve for delta G for mixtures 1, 2, and 3. All right, so I already got my expression to solve for temperature, but I must do one thing. I must convert my delta G naught units into joules per mole. Why do I need joules per mole? So that I can actually divide this number by 8.314, which is also in joules per mole. So now my delta G value is 3.4 times 10 to the 3. So my temperature is going to be negative 3.4 times 10 to the 3 kilojoules per mole divided by negative 8.314 times natural log of 4.0. I took the natural log of 4.0 and I get 1.386. I'm going to multiply that by 8.314 and I get 11.52565. So now I'm going to take my 3.4 times 10 to the 3, of course that's a negative number, and divide it by negative 11.52565. I get the overall temperature for 295 Kelvin. This is going to be the temperature that I use in my overall expression here for mixtures 1, 2, and 3. Now I can go forward and complete letter B, which is basically taking each of my mixtures, figuring out the Q values of them, because we're not going to be at equilibrium for all of them, and then use those values to plug in to solve for non-standard delta G. Let's continue on. So for mixture 1, we know that delta G is going to equal to delta G naught plus RT of natural log of K. But they also told us that mixture 1 is in equilibrium from what we saw from letter A. So that means at equilibrium, our delta G, or our non-standard delta G, is going to equal 0. Let's go ahead and verify that by plugging in numbers. So if I plug in my number for delta G naught, which we know is going to be negative 3.4 e to the 3, because we have to put it into joules per mole, right? I plug that in. I'm going to add it to my 8.314 multiplied by 295, which is the temperature we just calculated. I'm going to take that number and multiply by natural log of 4.0. When I go ahead and multiply all these numbers together, I get 3.4 times 10 to the 3, except it's a positive number versus the negative delta G naught value that we had. When we take our negative 3.4 e to the 3 and add it to our positive 3.4 e to the 3, we get 0, which verifies that delta G is going to equal 0 at equilibrium. Let's move on to mixture number 2. All right, so for mixture 2, we are not at equilibrium. Therefore, our expression will be delta G is equal to delta G naught plus RT natural log of Q. So to get our Q value, we're going to look at mixture number 2. We have 2AB, we have 3 A2 molecules and 3 B2 molecules. Remember, we're taking each of these numbers and multiplying by what's given, 0.10 atmosphere. So if I take 2 and multiply by 0.10, I get 0.20 atmosphere. Of course, I'm going to square this because I have 2 products. I'm going to divide it by 0.10 times 3, and that's going to get 0.3 for A2 molecules and also 0.3 for B2 molecules. When I take 0.2 and I square it, I get 0.04. When I multiply 0.3 times 0.3, I get 0.09. Therefore, my Q value is going to be 0.04 divided by 0.09, and that's going to equal 0.44. What I did next was take the natural log of my Q value, and I get negative 0.82098. Now let's go ahead and start plugging everything into our delta G expression. So we have delta G is equal to negative 3400, which we know is 3.4 times 10 to the 3 like we saw before for our delta G value, plus 8.314 times 294 Kelvin multiplied by negative 0.82098. So when I multiply all these numbers together here, I get negative 2013.56. So I'm going to go ahead and add my numbers together, negative 3400 plus negative 2013.56, and I get negative 5.4 times 10 to the 3 joules. So for our delta G at non-standard conditions, you see a lot of our units are going to be joules. Why? Because we have to convert our delta G naught value to joules, all because of our universal gas constant, which has the units of joules per mole Kelvin. Let's go ahead and move on to mixture number 3. Again, we are not at equilibrium, so we must take into account all the molecules that are present for mixture number 3. Again, for mixture 3, we are not at equilibrium, so delta G is going to equal to delta G naught plus RT natural log of Q. We're going to get our Q value based on the mixture in the scene that's given. We have 6AB, so we have to take 6 and multiply by 0.1. That gives us 0.60 that we're going to raise to a power of 2 because there are 2 AB molecules in our overall reaction. We're then going to divide by 0.1 and also by 0.1 when we, of course, multiply these two numbers together. So we're going to get 0.36 divided by 0.01, and that simply is going to be 36. I'm going to go ahead and take the natural log of 36, which is equal to 3.5835. Okay, folks? So now let's go ahead and plug everything back into our non-standard expression. We have negative 3,400 plus 8.314 times 295 times the natural log of 36, which we know is 3.5835. So when I multiply all these numbers together, I get 8,789.0. I'm going to add this value to negative 3,400, and I get a delta G is equal to 5.4 times 10 to the 3 joules. As you can see, this is a positive number. Let's go ahead and complete the rest of the question because they want us to say which one has the most positive delta G. All right, so for mixture 1, we got a delta G is equal to 0 because we're at equilibrium. For mixture 2, our delta G is negative 5.4 times 10 to the 3 joules. And for mixture 3, our delta G value is 5.4 times 10 to the 3 joules, which is going to be the positive version of that. So if they're asking us which delta G is the most positive, then it's simply going to be mixture number 3. All right, folks, let's go ahead and get into another example. This time we're asked again to calculate delta G at non-standard conditions. This question says the oxidation of SO2 gas is the key reaction in the manufacture of sulfuric acid. So you have 2 SO2 gas plus O2 gas is going to produce 2 SO3 gas. For letter A, they want us to calculate K at 298 Kelvin. They already give us the delta G naught at 298 Kelvin, which is negative 141.6 kilojoules per mole of the reaction as written. For letter B, it states that the container is filled with 0.500 atmospheres of SO2, 0.0100 atmospheres of O2, and 0.100 atmospheres of SO3, and kept at that 25 degrees Celsius. They want to know in which direction, if any, will the reaction proceed to reach equilibrium. And then finally, for part C, they want us to calculate delta G for the system that was in part B. So let's go ahead and get all of our juices flowing, right? We got to go ahead and get our non-standard expression. Then we're going to go ahead and start with letter A. So I have my non-standard conditions expression. But for letter A, I really won't have to use it because they simply want me to calculate K at 298 Kelvin. They gave me the delta G naught value. I already know what the temperature is. Of course, I know what the universal gas constant is. So what I can do is go straight into using my delta G naught expression here. That way I can solve for my K value. And then as I go into letter B, as you can see, we're not at equilibrium because we're given different values. I can then compare my Q value with my K value. So let's go ahead and get started and solve for natural log of K here by using the values given. All right, so to solve for K, I'm going to solve for natural log of K first and then isolate K after. So natural log of K is equal to delta G naught divided by negative RT. Again, our delta G naught value must be in joules per mole, so I'm going to multiply by 1,000. When I take my negative 141.6 and multiply it by 1,000, I get negative 1.416 times 10 to the 5th joules per mole. I'm going to divide that by my RT value. When I multiply 8.314 times 298, I get 2477.572. So now I'm going to take my negative 1.416 times 10 to the 5th divided by negative 2477.572, and I get 57.2, or the natural log of Kelvin is equal to 57.2. So then I'm going to take the natural log of both sides, and I simply get K is equal to E raised to a power of 57.2, which is going to be 7 times 10 to the 24. Now I have a K value. So for letter B, we're outside of this K value. And so to determine if a net reaction will occur, we have to find Q from the given partial pressures and compare it to the K that we just solved for in letter A. Once we compare the two, we can be able to again solve for Q and then continue on with the overall expression. So first, I'm going to look at my reaction as given. I have my product, and I'm going to divide it by my reactants to get my Q expression based on the values that are given in letter B. So they already tell me that for SO3, I'm going to have 0.100 atmosphere. So I'm going to have 0.100 squared because there's two of them. I'm going to divide that by SO2 value, which is 0.500. I'm going to square that. I'm going to multiply that by my O2 value, which is 0.0100. So when I take my 0.1 and square it, I get 0.01. When I take my 0.500 and square it and multiply that by 0.01, I get 0.0025. Therefore, my Q value is 4.00. Now that I have a Q value, I can compare it to the K value we got before. So my K value was 7 times 10 to the 24. Because Q is very much smaller than K, our overall reaction will proceed to the right. Of course, it's going to be spontaneously proceeding to the right. And so for letter B, when they ask you in which direction, if any, will the reaction proceed to reach equilibrium, you're going to say to the right here. Now, for letter C, it tells us to calculate delta G, which is non-standard, for the system in part B. So for this system, we already have our Q value. We already know our temperature, which is 298 Kelvin. We already know the universal gas constant, and they already gave us our delta G value for this overall system. So all we're doing is plugging and chugging for letter C. Let's go ahead and get to it. So we know that delta G is going to equal to delta G naught plus RT natural log of Q. Now, we have to kind of consolidate here because we have to look at units. Again, our delta G naught is given as kilojoules per mole. I automatically just put this into joules per mole here, folks. So I multiplied that number by 1,000. That's how I got negative 1.416 times 10 to the 5th joules per mole. I could have easily went ahead and converted my universal gas constant from 8.314 joules per mole to kilojoules. Why would I do that? Well, because we're at 298, we're technically in standard conditions. And if we're in standard conditions, then we know that our delta G naught usually have units of kilojoules per mole. As we've seen, our non-standard usually have units of joules per mole. So for this question or this answer here, we will see the units be kilojoules per mole simply because we're at 298. If we weren't at 298, it will be joules per mole. Okay, folks? So what I do is I just go ahead and convert my delta G naught value to joules per mole. And then once I get my overall value and answer, I just simply convert it at the end. So my delta G naught value is negative 1.416 times 10 to the 5. I'm going to add that to 8.314 multiplied by 298 multiplied by the natural log of 4.00. So again, I'm going to have negative 1.416 times 10 to the 5th plus 3,434.64. When I add these two numbers together, I get negative 138,165 joules per mole. Again, because we're at standard states or because we're at 298 Kelvin, not particularly standard state conditions. Because we're at 298 Kelvin, I can then go ahead and convert from joules per mole to kilojoules per mole. So I go ahead and divide this number by 1,000, and I get negative 138.2 kilojoules per mole as my final answer for letter C. All right, folks, it's all done now. None of our ghost remains exist. They've all been salted and burned. And so for a final farewell to our journey in Mystic Fall, let's go ahead and summarize another way to look at the meaning of spontaneity.